Hello everyone, my name is Shihan Zhao and my group member is Chuchen Jiang. This is our project part 2. Our presentation topic is about asymmetric multiprocessing ASMP and operating system scheduling. In this presentation, we will have 4 parts. Part 1 is introduction, part 2 is big.LITTLE architecture context, part 3 is completely fair scheduler, and part 4 is energy-aware scheduling. And Chuchen Jiang will introduce history of the ASMP at first.
So back in the 1960s and 1970s, the concept of asymmetric multiprocessing as ASMP emerged as a cost-effective way to increase computing power by adding more CPUs without incurring significant costs. This type of architecture predates the advent of symmetric multiprocessing (ASMP). For room-sized computers at that time, a cost-effective way to increase computing power was to add another CPU. Since these computers are already close to the fastest speed available at that time, 2 standard speed CPUs are much cheaper than building a new CPU that runs twice as fast. Additionally, adding another CPU to a system is cheaper than buying another complete computer, which does not require another entire set of peripherals, double the footprints, and it also eliminates the time to transfer data in between. The board of B5000 shown in the lower left corner was the first prototype of multiprocessing in one system. It introduced the concept of a secondary processor called Processor B, which has limited operating capabilities and no peripheral connects. The CDC6500 shown in the lower right and its successor CDC6700 established a scheduler model in which all user applications ran on the central processors, while the operating system scheduled user applications on the peripheral processors. Since then, the symmetric multiprocessing (SMP) has become the mainstream choice. However, in the past decades, in order to solve the contradiction between power consumption and the performance in mobile platforms and data center applications, the concept of asymmetric multiprocessing has once again received attention.
In the introduction, I will talk about what is the big.LITTLE architecture at first. The big.LITTLE architecture is a technology. It contains 2 kinds of cores, large and small cores, and it is a heterogeneous multi-core processing technology proposed by ARM. Within each chip, there are better performance processors. So in the figure, it is like A57, and there is another core named Little Core. It is more efficient, but its consumption is less. In the figure is the A55, and it can be considered as the Little Core. Why we need big.LITTLE architecture? That is because there are different kinds of tasks, and the bigger cores are used to handle computational intensive tasks such as games, and the small cores are used to handle tasks that take a long time to run but require a small amount of calculation such as calls and videos. Based on different tasks, using different cores for processing can ensure that the computation can perform high-performance computing while reduce daily energy consumption as much as possible. That's the original intention of the large and small cores technology design. And And there is a most important thing for the big.LITTLE course, that is how to combine. In the history of of the big.LITTLE course development, there are three kinds of way to combine big and little cores. The first one is cluster switching, and cluster switching refers to a cluster for large cores and a cluster for small cores. Every time you switch between large and small cores, you need to migrate all process on the large cores to the small cores, or migrate all process on the small cores to the large cores. Only one cluster of the two can be running at the same time. The disadvantage of this are the high cost of transfer and the difficulty of scheduling. Obviously, that is because the running program of the computer is relatively complex and it's difficult to set. There is a time that only have the high performance, high calculation process, or only have the process that need run for a long time, but it don't need too much calculate. So this cluster switching is not a good choice for the big.LITTLE architecture. And after that, there is another way of switching, is the in-kernel switching. In IKS, little and big cores are split into pairs. The operating system will detect the performance and the consumption required by the program during the running of the process in order to allocate appropriate core according to the needs of the process. Compared with cluster switching, this method allowed large cores and small cores in the CPU to run at the same time. However, in each pair, only one core can be running at the same time. This leads to the fact that there are always general cores in the CPU that are not working. This still greatly affects the efficiency of the CPU. And nowadays, the large and the small core structure successfully used on ARM, Intel, Apple M1 and M2 chips is heterogeneous switching, HMP. This kind of way to combine big and little cores allowed each core use simultaneously. So this obviously greater improve CPU utilization and efficiency. That is because you can use all cores at the same time. But for different tasks, core allocation has become the main issue that needs to be considered in this architecture. In the next part, we will focus on explaining the scheduler of the large and small cores architecture. For the Linux scheduler, all of the Linux scheduler, they use a CFS, completely fair scheduler. The goal of completely fair scheduler is even distribution of task load across cores. The task ready to run should quickly find a core to run on, which means I don't want to spend a lot of time on scheduler. So I want to schedule each process as far as possible. So the implementation of this scheduler is sorting tasks in accent order by CPU bandwidth received. And after that, we will build a red-black tree. This red-black tree are used to streamline the process. And then the leftmost task of the tree is picked up next, and then it has the least span execution time for operating system to scheduling each process. But there is a limitation, is that it implies all of the core are the same, and that means there are some obstacles for the big and the little architecture. The first one is CFS is not really applicable. to big.LITTLE architecture because it considered all cores as the same. And however, the big cores require carefully treatment because we want only run big cores when it is really needed, which means only the process is too difficult or it needs more performance of the core. At that time, we will run the big cores, but if we use mainline CFS, we will not consider that. We will think, okay, no matter this process is difficult or not, we will allocate it in the big cores. So detection of such a situation is a problem to solve. And there are another way is task packing problem. So this problem will cause the CFS is not good to use in the big.LITTLE architecture, and we want to have some another principle to limit to make this obstacle to overcome this obstacle. And in that case, we will introduce the EAS energy aware scheduling.
The energy-aware scheduling, as EAS, gives the scheduler the reference to predict the impact of its decisions on the energy consumed by the CPUs. EAS relies on an energy model, EM, which is provided by the hardware implementation, that is, of the CPUs to select an energy-efficient CPU for each task, with a minimal impact on its throughput. The goal for EAS is to minimize energy cost while still getting the object done without significantly impact the system throughput and reach the good enough performance. So in the graph showing below, there's multiple lines, which is the performance and power curve for E core and P cores. And the system performance selection from the scheduler is the outer line, which is E in the bottom and P in the top. The goal is to maximize the performance instruction per second divided by the power in watts, which is equal to the minimizing the energy, the joule per instructions. The energy-aware scheduling alters the assignment of completely fair schedule EM to make better scheduling decisions by using a much simpler design to minimize in choosing the most energy-efficient CPUs for tasks using the knowledge of CPU capacity. Performance per power is a line and is shown in the bottom right, the energy model list for the E cores and the right part for the P cores. In each, there's multiple entries of their operate like the sweet point for the CPUs to get performance in certain capabilities power. So as the left front is and energy cost of 50. So bottom points in the E core curve. During task wake up, EAS leverages the EM along with the per entry load tracking (PELT) signals to select an optimal CPU. The function selectTask_RQ_fair invokes find energy efficient CPU, which identifies the CPU with the highest available capacity in each performance domain. This choice helps maintain lower operational frequencies, therefore saving the energy. The decision process evaluates if moving the task to a new CPU will be more efficient compared to its previous CPU. The compute energy function estimates the energy impact of migrating the working tasks, simulating the new task distribution across CPUs. The EMPD energy API from the EM framework calculates the expected energy consumptions for each performance domain based on this simulated distribution. So here's the EAS example. We assume there's a fake platform with two independent performance domains composed of two CPUs each. CPU 0 and CPU 1 are little core CPU. CPU 2 and 3 are big core. The scheduler must decide where to place a task P whose utility average is about 200 and the previous CPU is 0. The current utilization landscape of the CPUs is depicted on the graph below. CPUs 0 to 3 have each a utility average of 400, 100, 600, and 500 respectively. Each performance domain has 3 operating performance points, the OPP. The CPU capacity and power cost associated with each OPP is listed in the energy model table. The utility average of P is marked as PP. The energy model EM, which represents all the OPP's cases, are listed here. The table has E cores with capacity of 170, 341, 512, and P cores with capacity of 512, 768, and 1024. So we distributed the PP function into different cores. The right 4 graphs are the estimated function cost for each scheduling scenario. As you can see, in graph 1 and graph 4, the OPP increase, therefore the energy cost and the operating points is changed. This slide shows the total energy cost estimation with formula. The energy cost is the sum up of each CPU's energy cost, and for each energy cost it is the utility percent divided by the capacity of each CPU's times the power rate at the OPP the capacity tells with a parameter of k. The parameter of k is r equals to 1 as it stands for there's no preference of allocation for the system. As you can see, the allocation of PP to the CPU little core 1 is the minimum total energy. So which means to allocate PP into CPU 1, the system itself will reach the minimum energy cost. There's other scheduling reference that is needed by the Linux system. For x86-64 and the IA32 architecture, the Intel introduced their Intel Thread Director and hardware feedback interface for the Windows system. And there's another thing called the cluster-aware scheduling that is for the 6-bit ARMS architecture, and it is already merged into the Linux mainstream 5.16. This is the end of the presentation. Thanks for your listening. If you have any problems and comments, leave it below or in Piazza. Thank you.